Waste not, want not. Okay.
What a title.
Yeah. Yeah. As you know, me and the dad jokes there. Look at your application. It is so important to think about your application and what you're doing to not put in joints that you do not need. If you need this general purpose one that's going to be working absolutely everywhere, maybe you need to put it in there, but it's going to come with a cost. You can see that the pelvis, because of the unlocking of the hip, is no longer horizontal to the ground. That pelvis is like doing this as they walk. And yet the torso remains horizontal. And so you can see the movement going through the waist on the X direction there. That X axis turns it because as those abductors and everything are going around, the pelvic bone is doing this, and you got to get a little bit of movement if you want to keep it level. So if I'm going to be serving drinks on a tray, I don't want to be doing this. I was looking at, what you can do with some of these different designs. And again, looking at Unitree and what they're doing with, and I think this is the full waist that they have here. And this was them doing, and it might've been like the first time this trick was done. So I think they, for that, it looks like they were using all the 3 degree of freedom waist. No doubt about that. If you want to do dancing, surely you need to have something there. Now, this is engine AI, and I don't think they have any degrees of freedom. I'm looking at it, and sometimes your eye gets tricked to thinking that maybe they have a Z, but I am not seeing any movement at all in the waist. Look at these things and come up with a decision and think to yourself, how much do you use your waist and all the activities you do? How much of is it actually in there for doing some things? Now, obviously, when I'm trying to fix the plumbing, under the sink, man, now I got to get myself the torches to get in there. That might be very important, but for everyday kind of things, maybe not. So, all right, Mara, how was your week so far?
It was great. As always, stressful, but we managing.
Good, good, good. Yeah, I had a little break there, but somehow I think we backed up enough podcasts that you were able to kind of get them out in enough chunks. So today we're going to address an issue I kind of promised in the end of the last one. And unfortunately, I've been kind of procrastinating on getting it out. And but I've got my thoughts in order, and so it's just going to help me get the whole thing out as actually a post that I hope will be beneficial to everyone. So the first thing I want to do is go ahead and start out the slide and let everyone know what the title of this is going to be, and that is "Waste Not, Want Not."
What
Okay.
a title.
Yeah, yeah. As you know, me and the dad jokes there. And so I'm going to explain everything that's kind of going on in this picture because obviously it's pretty busy, and it's a sequel to this post I put out a little over 2 weeks ago that I just kind of threw together. I wasn't expecting to do very well. It performed really bad the first couple hours, and then China woke up. The whole Far East woke up, and they started looking at it, and then suddenly it just started getting lots of views and like I think at this point 567 bookmarks, which means okay, a lot. So it got to the right audience, and I kind of promised like, well, we should do a follow up and sequel. And the reason why I'm procrastinating is that this thing did so well. You know how hard it is to make sure the sequel is as good as the original. So I'm kind of again wasting a lot of time on coming up with it. And the last time we ended up making a podcast out of the post. Now I'm going to be basically making a post out of the podcast. It's going to switch around. So thank you for helping me to organize my thoughts here a little bit. So, the whole idea back then was looking at what the different kind of designs are in the hips and how they've kind of changed and what are the different strategies going on. And we're able to sort of see that over time there's a consensus on what is the best kind of hip design to get out there. And so I was saying, okay, let's do the same thing with the waist. Is there kind of a consensus building there or not? And, well, it's going to be a rather interesting conclusion. It's going to be a different conclusion than we've had here. And so before we get too far into it, the first thing you did when we talked about that is you were seeing us having these different initials up there, FAR and RAF and everything else. And what does that mean? And basically it was borrowing the nomenclature from biomechanics and when we talk about the movement of the hip and the leg and what it's doing. And then you've got flexion extension and you've got abduction and you also have rotation in there. And so I use those abbreviations. And because the human body, um, well, has a ball and socket joint, but the robots aren't using one. They had to kind of organize the rotations in a particular way. So we looked at that to kind of address how they are emulating the same kind of motions and what's going on in there. And a comment that kind of came out of it that I want to highlight early rather than waiting to the end came from Lars Nystrom. And you know, he says right here, an effective way of turning is by turning 1 foot 45 degrees putwards and take one step forwards or backwards. I haven't seen any of our current robots doing that. They just shuffle a bunch of small steps. I have suspected they don't have the hip mobility for that. One missing dimension of hip mobility, I have thought. Okay, so Lars is absolutely right about that, and we didn't talk about it in that particular episode because we're really looking at the organization of the joints. And I probably could have maybe explained a bit more exactly what's the importance of flexion and abduction in the rotation in that scheme. Flexion is basically what you need to be able to walk, to stride forward. The abduction is useful for when squatting down, stuff like that, but also kind of maintaining your balance when you're perturbed or might be falling over, that your legs basically kind of spread out a little bit. Or if you're lifting something heavy, you'd like to get that. I mean, or if you're an uneven surface, there could be a variety of reasons for it. And then there's the R part of it, the rotation, which may not be so obvious if you're just walking straight. And it probably plays some role, a little bit in stability and balance, but it's such a minor role that a lot of designers might kind of question, do I even need R in there? And the thing is, they all decide it. I mean, it's like the only question is what the order of operation should be, but they all agree you need to have flexion, you need to have adduction, you need to have rotation. And what Lars is talking about right there is that the rotation is what's very important to moving, to being able to change direction. And right now, we see everyone kind of pitter patter with their feet like this. We're trying to change direction, which is driving me crazy. It's like, wait a minute, why don't you do it the way we do? And again, I've told everyone, you're a biomechanic, okay? All you have to do is like look at what your body is doing and you can figure this stuff out. So go for a walk and start to take a turn. And the thing you're gonna know is exactly what he says is that you're walking along like this straight. And then when you turn, one of your feet goes this way. And this is the importance of rotation. So you kind of rotate out. And then as you lift this foot up, you then kind of counter rotate what you have there to bring the other foot back around. And depending on how much you're turning, you might even turn that one inward and keep on doing it to go around the circle. So it's very important. And he asked you a question like, why aren't we seeing it? Did they not put it in the hip mobility? It's like, it's actually there. The mobility they need is in the hip. The problem is, it looks like no one's bothered to kind of unlock that yet. And again, I want to bring this up because we already talked about in the in out episode of going through and looking at the joints and what the importance of the joint is and what it does. And if you make a decision to take it out or put it in, you better describe what it's there for, what it's good for. And if you can't, then maybe it doesn't belong there. Or let's say if you can't argue the reason why it's not needed, maybe it should stay in there. And a lot of it seems like they haven't quite used it yet. And a lot of it comes down, they haven't been able to unlock the joints yet. So we might remember about 2 years ago, there was this video that was included in the AI Day showing the evolution of the walking. Okay, let me turn off the vocals there. So they were sort of showing how they would, probably through RL training, and it's actually taken a while before Tesla. I mean, they've only recently started to do RL of getting the hips to unlock. And when you get that full mobility, now that's a straight line. We're not saying it's turning, but you begin to see that when they're first starting out, they weren't using the abductors or anything like that. That the hip is like really not doing very much there at all. And then eventually, as these get trained and they get better in the stability of their systems, they go on. Now, to see kind of a more recent, better example, because that was just a CGI animation, is Figure released something last week showing the RL that they've done for the walking. And this is not CGI. This is the real deal. And if we kind of look at this, we will see that there is a lot of sway in the hip. There's a lot of movement going on there. And so it tells you, wow, it's pretty important that when you let the AI training go through and figure out the best way rather than a bunch of guys coding, which is kind of how the walking was done before. Everyone was kind of coding that. It improved a lot of things. One is to get more of the straight knee. They're a lot faster than before, but there's a lot of hip action in there, which is very important to walking. And that rotation in there, there's probably a little bit in there. It's very subtle, but it's there. And it's very important to being able to change directions. Absolutely. No doubt about that. So now we're going to kind of switch gears and we're going to move over to the design of the torso and like how important the torso is. Now, these may seem like separate subassemblies and separate units, but they need to be integrated. You need to look at it holistically. If you think that you can you could design those separate from one another, you were absolutely wrong. Because again, if we look a little bit at the figure video, we're going to see that a lot of the swaying that's going on there is not just in the hips, it's also in the waist. And the question is, how many degrees of freedom do you really need in the waist to be able to pull this off? Do you need any of it? Do you need more than what's there? What's missing? And that's why it's going to be important looking at this as a compendium first, as looking at the hip design. And in a way, it's like, I almost should have made it one. We're going to look at all of it, but then it would be like a 3-hour episode. And I don't anyone wants that. So the first thing is kind of a reminder is that the way the human hip works is it's a ball and socket joint. So that's basically what it looks like. But it's very difficult to actuate that unless you have actual musculoskeletal system like we do, with muscles that are being able to pull in different directions to actuate it. And it's very hard to do that mechanically. So we've settled, at least for the hip design, that you go ahead and you stack a bunch of motors together to get the same kind of effect. Definitely different. It's not exactly the same, but it allows you to have those FAR degrees of freedom as are considered necessary. So if we proceed ahead and say, okay, let's take the same approach on the torso or the waist, and the reality is our waist is not a ball and socket joint like our hip. It's a segmented spine with many degrees of freedom that allows a lot of flexibility. And this would be way too complicated to try to duplicate in a humanoid body. And so what we end up doing is we decide that, well, rather than having this kind of full flexure through here, the end result is it causes like my shoulder up here, your clavicle to rotate a certain number of degrees. And maybe that's all we have to do. And then we can kind of come up with a center of rotation somewhere down about our waist. And again, if you look at like a lot of these figures that you get that artists use and stuff like that, that's exactly what's going on here, right? You get kind of you're just rotating around the waist and everything else remains kind of rigid going on up there. Okay, so let's get into terminology. So if you look at spine movements, they're usually biomechanics, or if you go to physical therapy or something like that, they'll use the terminology of flexion extension, which is basically talking about the same degree of freedom, just that one's positive, one's negative. Then they have rotation, and then they have lateral flexion. Uh, and I don't like these terms because, you have flexion here, you get flexion there, and lateral, and it's like, it's going to be a bit confusing. And I don't want to go to the yaw pitch roll term because everyone's abusing how it's used. There's actually a proper definition for it, but it's surprising how everyone kind of uses it in a way that will get everyone kind of confused. So what I'm going to do is to say, okay, forget about it. What we're going to do is we're going to go by the axis. So if you're walking straight ahead, that's your x-axis. Okay, so over here, lateral flexion is a rotation that you do about your belly button, which, if you want to think about it, is when you kind of lean left and right. Okay, and then the rotation is your vertical axis, and sometimes it's called like torsion, moving around your torso with a little bit of torsion there, or rotation about that. And then you have the flexion extension. It's basically, it's bending. It's you're bending. It's like, if you look at this, it's almost like getting ready to dive in the pool. It's that kind of bend that you would do. And so I'm going to refer to those axes. So the axis that goes this way across your body is Y, straight ahead is X, and up is Z. And so we now know that, again, because what we had to do with the hip is we don't have a ball and socket joint, so we have to do a series of rotations together. And so what I talked about with going at the hip is that, okay, you get the series of these rotations, but you can do them in any order. And this is something that Euler figured out centuries ago, that if you want to describe a rotation, there's a variety of different angles named after him, the Euler angles, and you can do them in any order. Now, his set was I think way more complete. It was like 24 possible combinations because you can do a rotation two times about the same axis if you want, after it's been rotated. So in our case, we can say, no, that's not going to happen. They're all orthogonal axes, and we can organize these FAR or rotations in any permutations that we want. And that means we have 6 possibilities of being able to do that. So what about for now doing it for the waist? Well, kind of the same thing, except rather than calling it FAR, we're going to just call it XYZ. Okay. And so we look at all the permutations that you have here. And again, you shouldn't be surprised. There's going to be 6 possible combinations that we have here. Now, it turns out with the hip, everyone agreed you need to have all 3 rotations. With the waist, it's not so clear. So the actual design space that we have for this is going to be a lot bigger than just the 6 that we have here. Okay. Because in some cases, they may be adding an extra one, which we're going to see. There's one case they added one more, and in many cases, taking them away. And again, some of these strategies of using like a parallel kind of kinematic mechanism also kind of makes a little twist on the type that's in there. So when I look at all the possible combinations out there, there seems to be about a dozen that may be there. It's not fully populated, but we see that the design space is getting, let's say, more attention from the various vendors than we did with the hip. And we're going to come back to this in detail, but let's go ahead and remind everyone that this is how we kind of classified all the hips that are out there: FAR, REF, and, ARF, and RAF. And there's a couple that aren't shown up there because I couldn't find any examples. So even though the design space was much bigger, it wasn't really completed because a lot of the designers figured out right away, that's not something that we want to tackle. And let's see. Okay. Now, did I accidentally unshare something here or oh, okay, we still have it because I just did something to make my window go away, and so I'm not seeing it right now. So where'd the window go? Where'd the window go? Let me go ahead and bring up. Okay, there it is. All right. So now let's move ahead and kind of look at what we are going to do here. Now I decided to use actual axes and colors and stuff like that to hopefully make it easier for everyone. So here's an example of a ZYX waist, okay, where the first rotation is about the Z, which is the blue axis. It will always be blue. And then we have this Y rotation here, followed by X rotation, which is up about here. So that X axis does not intersect the Y and the Z axis. So there's a little bit of an offset there. And this was for a GR1. This is their first attempt on it. And it's the only one I've seen out there like that, which is why they get to take that space. Now, if we go again to, starting out with the Z class here, we have what is a fairly common one, which we sort of first saw in figure and is now common in a lot of the others. And this is what I call the ZXY. The reason why I call it XY without the dash is because they're using that parallel kind of actuation strategy. And technically it is kind of XY because there's a cardan joint down there. And the first rotation of that cardan joint does seem to be X. And the second a Y. The cardan joint is basically a type of universal joint. It's like you've got two pin joints basically, self-intersecting through there. And you'll see everything is well centered there. And the reason for this parallel actuation strategy is that rather stacking two actuators, on top of one another, you can kind of put them side by side, but then you need a linkage mechanism to do that. Then we go to another design, which is common. We'll see it in Optimus. We also see it in Figure and a few others. And this is like the YXZ, so we had ZYX and now we have YXZ. Except you'll see I made the Y lowercase. And the reason I made it lowercase is it's really part of the hip. It's not part of the waist. But it's a redundant joint. And it's one of those things that you can actually use it for either that you want. And again, this is why I say that your hip and your waist design can be integrated together. And if done cleverly, you can almost eliminate a joint because you realize, hey, the two of them are the same. And it's a question of whether you need to have that extra degree of freedom up higher, which would give you, let's say, a bit more flexibility. Then there's the Unitree H1, which again is like in that lowercase y category. It's a YZ. And if you want to think about it, it's just like they're really just a Z, and they're following up by getting the Y out of their actuator here, which is the flexion. So they're using the flexion for that. And then the P&D Robotics, which is one of my favorites because when they came out, their design had so many novel things about it. I really liked it. It's like, okay, these guys are thinking on their own what they want to do. And this is the only example I could see of like XYZ. Okay. So we've got the first rotational axis over here, which is, the red axis, which is almost in the center line. It's just a little bit above where the flexion is. Actually, if you look at the way the flexion is down, because they have this unequal angle there in the pelvis, if you were to take those axes and go back, they intersect exactly where the x-axis is, which is a rather interesting thing to see. And then they have the next is like a Y rotation, which is oh, did I? Yeah, I have to fix this before I put it out there. I'm missing the arrow that should be in here.
Like
But if
green
you see
one, you
my
mean?
cursor, yeah, the green one. So you see where my cursor is going back and forth here. That's where um, the Y rotation is, and then you have like also a Z rotation, which is like above that. So it's right above that. So it's an interesting organization of being able to do that for the spine. But you see, it does take up a little bit of space. And then we have agility digit, in which I'm giving it like the lowercase y. I could just say they don't have a waist because technically they don't have a waist. Everything here is in the hip. There is not a waist, but they have something here. And we're going to look a little bit more at the agility design because I think there's a lot to be learned here about a waist by not having one. Okay. And whether it was a good or bad decision. Hmm?
What is the advantage of not having
Oh,
waste?
lots of
Or
it. A lot of advantages is one, two, three less motors. Less mass, less costs. And the real question of your application was kind of so I would look very closely at what agility has done to Digit and their decisions and why they did that. And these are well informed decisions that they've done, and they're looking at a particular application where maybe it makes sense. So you might say that okay, they're working in logistics, working mainly on flat floors, all this stuff maybe it's absolutely perfect for that. They didn't over design the thing, but there may be search and rescue. You got to crawl in these weird places, something like that. And then you might say, oh, they got to have the waste in there. But I think it's basically a clinic when we look at what they're doing and the decision that they made there. It's not like they said, oh, we don't know how to put a waste in there. They look at it and we're gonna see as we go along how this. And then finally, there is like the seventh one that's in there, and because seven's a prime number, I couldn't fit them in there in a nice array. And this is from Sanctuary, where they have a ZYXY. Okay. They have two rotations. Now, they actually do that in the head. We didn't really talk about that as a design possibility when we went through our Decimate bot. In that, at one point, Sanctuary actually had 5 degrees of freedom in the head. Because you really think about it, you get kind of like three down here in the neck, another two up here, and that we a lot of times we just say, "Oh, just forget it. Just the one down there is gonna be good enough for the head." But if you really want to get it, you might want to have a little bit more. And they felt that was important for having more human-like qualities. And that might be the same thing here, is that they've got a very, very flexible spine. You might even have like another Y in there, like one of those lowercase Ys that comes from the pelvis area. But I'm not giving this too much attention because we haven't really seen this walking. I mean, we haven't seen the reality. This is more of a CGI of what they plan on doing someday, but they haven't really shown us doing this. And the other thing is, most they seem to be doing a lot hydraulic, and I'm not sure where it's hydraulic and where it's electric and everything else. And so, to really do apples to apples, let's talk about all electric bots because you can cheat a little bit with hydraulics and get away with smaller actuators and everything else. It gives you more possibilities, but then you have literally the baggage of being hydraulic. Okay, so I'm going to kind of go through some of the individual ones that are out there because I collected a lot of them, and I think they all have some very interesting things to say about the design. Adam, well, they're here partly because they start with the letter A, and it was like a unique one that comes from PD Botics that they've done a lot of things that I like. They were one of the first ones that I could see an anhedral angle down there, pretty strong dihedral angle up here in the shoulder, and some other things that we're going to use in the shoulder episode when we talk about that I think are some interesting things to point out. So, but again, it does take up a lot of space. You see the space that's left over for the torso is kind of minimal at that point. So that's eating into your battery and how long you would be able to run. This here is again close up of what Fourier did. Or sorry, this is not Fourier. This is Unitree. And you'll see right up here is where the rotational axis is for that. Now, I'm not sure if the servo is above this or below that. I would think it's down here. So you leave up a lot of room, but basically the joint is right there. And the big question is like, oh, okay, they don't have the X. They've taken that out. Surely it must limit them. Oh, really? They remember they were the first ones to do a backflip. So if you think you need a full waist, think again. And I'm not even sure that you needed the Z for this. All right. So so remember, they were able to get a backflip out of this thing. So look at what they've been able to do with some of these different designs. Now, interesting that on the next version of the Unitree bot, they basically, this is now the G1, they've added more degrees of freedom here. And they have a very similar mechanism, what we saw in Figure, and we'll see also Atlas is using, where you get that parallel mechanism here, that this is a ZXY in there. And so they have that. However, this is the high end level of the G1. This is like the one that's $64,000. If you go to the $16,000 one, you'll notice that waste mechanism isn't there anymore. It's kind of missing. We can get a little bit of a close up of it. You can say, oh, wait a minute. It looks like it just has a Z rotation. And so they've been trying to figure out themselves what's the best design, and maybe have decided that, two versions is fine. They're going to go down that route, that they're going to have these because they end up showing kind of as an option. Now, this one here kind of confuses me. I think this is the low end G1 kind of because it doesn't have the full wrist in there. That doesn't quite like look like the full waist, but you see it's kind of missing a little bit in there. So I'm not sure if that's the full one. And then you see if you go there, and again, props to Unitree is they are very transparent with the amount of information you can find on their website and the technical details, so you're not guessing. Um, and they also use the term degrees of freedom correctly. Yes, someone paid attention in engineering class. They get it right every time. All right. So so the waist degrees of freedom, they talk about that there's one that comes with um, the base model, and the high end one, it's one plus two additional ones. So they have either 1 or 3 degrees of freedom here, depending on how you want to look at it. And and then let's take a look at some other examples here. Here's Atlas one. So Boston Dynamics first just had the Z, so it's just pure Z, and then so you can call it a YZ because there's a little YZ down in there if you want. Um, and and then when they went to the new Atlas, they decided, well, we need all those degrees of freedom. So again, similar type of mechanism where you have the Z rotation first, followed by an X and a Y as a parallel structure that's in there. So that's the new Atlas. And and once again, I overclick something here, and let's bring that back up. So and now Engine AI, what's rather interesting, they've gone through two series here. And the first one, they made a big change in the hip. We kind of talked about that, how their hip design changed quite a bit from that they were, I think they were RAF to now FAR. And yeah, and they've been very good at walking. I mean, their walking videos can be pretty good. And here I have not seen any movement in the waist. And same here. So my feeling is that they don't have an actual waist, and that's instructive because you're looking at these different things. They're able to kind of reposition the torso because you don't necessarily need the waist to bend the torso around in different directions. You can actually do that with your legs, and agility is going to show us how that's done. Uh, so uh,
There's no waste here. There's no waste here.
There appears to be no waste. And again, if you want to say, oh, well, if you don't have a waist, you obviously can't do anything with it. They did the first front flip. So, so we had one that just had the Z that did a backflip. And now we got Engine AI kind of showing. I was like, hey, look what we can do just, with none. We can do the front flip. Okay. So again, it gives you an indication that, how important are these joints? I am not sure. Now, to take it a step further here is that after the front flip happened, Unitree said, "Wow, all right, we're going to show the world's first side flip." And look at the bot that they use. I think that might be they only have a Z rotation. I was looking at it really closely. I think it's only the Z. I don't think they have the XY in there. So it looks like, and I would have thought that'd be important because you think bending and everything else would be in there. But when I look at it, it looks to me like it's just the Z axis only version. So, yeah, you can do a lot with not all your degrees of freedom in the waist, surprisingly, to something else. So again, here's a close up of the figure waist. So kind of remind us of that kind of waist mechanism, and to see that you build these things, you learn from them, and then you build your next one differently based on lessons learned. And so they pivoted there a little bit, um, pivoted or pivoted less. I'm not sure which. There's a joke in there somewhere. Uh, and then again, if we look at the Optimus design, this is the original Bumblebee, and we can see the rotations that they have here. That they have the X first, then followed by the Z, and that's basically the same order of operation in the Gen 2. So Bumblebee Gen 1, Gen 2, that all is using the um, same configuration there. And part of it is, again, you don't want to add an extra degree of freedom in here if you don't want to, otherwise kind of bump that up. And that way they have a lot of room in that torso cavity to be able to fill it with electronics and to fill it with batteries and everything else. But it comes with the downside that their y-axis is way down here. So the y that you use for the redundancy, the little y is here, whereas if we go, figured out how to bring it up a little bit higher in their design. So it's actually closer to the waist than we're being able to see with the Optimus design. So those are some of the trade-offs you have to think about when you go into it. So again, here, this is the GR1 from Fourier, and this is their new design. And so they basically eliminated, it looks like, a lot of the joints. They just went with Z. So they're going straight to Z now. So rather than, see, what was theirs was ZXY or something like that. They've now gone to one where they decided, hey, we only need one. And again, they're going to an interesting pelvic design here that has a really what appears to be a rather strong anhedral angle here in the pelvis, bringing that down. So again, some interesting lessons learned there. This is the UBTech Walker, and it has no waist that I can tell of. I'm looking here. It's a rather interesting design that they have this is basically an ARF. So this is an ARF design, and you'll see that's way up there. So partly because they wanted to get that Y rotation up as high as possible, but you see a lot of that's eating in there. So there's like no room left over for a waist.
So
So
just quickly, it seemed these two possibilities, either they are the waist or the RAF. It seemed that that's what they're playing with. Or
yeah,
I'm getting
yeah. And again, I think if you're going to like this ARF design here, you're losing a lot of your waist area, and it seems that that's another reason to go with FAR. So FAR is far and away the best way because it's a very very compact um, the pelvis area, and things just naturally fit into place. And it also means it kind of integrates really well with your waist, and you can use one, the flexure as your y axis, so you can eliminate one of the axes you need there. Otherwise, you it won't be rotationally equivalent, functional enough. The main thing is everyone is just like getting all uptight about the fact that we have to carry those actuators. Those actuators are going to be really bit bulky and heavy, and we don't want the flexure to be able to do it. So that seems to be the point. But again, everyone moved away from it, and then you could see that's like the majority has moved off in that direction. Okay, so now let's come to our friends from Agility and what they've done, and they're going to get a spotlight when we talk about shoulders as well. Not this particular one, but like an earlier generation. Um, uh, there's not that much to talk about shoulders. I mean, there should be a lot to talk about shoulders, but unfortunately, they haven't given us that many options. But that's for another episode. Anyways, we're kind of looking at this, and you can see it doesn't look like there's any waste. So all these actuators and everything you're seeing here are for the hip design, and that they have basically the abductor going back this way. That's A, and then got this going down here, which is a rotator, which is going to be your R, and then finally the flexure F. So it's kind of an ARF design that they have up here. You see, it does kind of come up high into the waist area there, and there's no other actuators for being able to do anything in the waist. It's absolutely there. So you must think, all it can do is stand straight. That's all you're ever going to see from the spot. And then you look, I caught this image from one. It was like, well, I'm looking at that torso. That torso is not vertical. From here to there, you can see it's able to lean forward a little bit or bend. Has a little bit of possibility here because sure enough, I mean that's what that flexure axis is for. That's what we've all talked about, that lowercase y. It's there, so you want to bend forward. So they, right out of the gate, they realize, hey, we don't need that. We can get that from it, so that shouldn't be a problem. But the question is, what about the other stuff? Back and forth. If you need to do that, and if you need to twist around, wouldn't that be rather important access to have? Well, let's go ahead and see. This here is something I caught um, at. They did a live stream about a week or so ago from ProMat, showing them on the shop out on the floor on the trade show floor, going around, moving the boxes and everything. And I ended up catching, and there should be a video. I'm trying to get my cursor over here to get to persuade it to start. Okay, there we go. So now what I want you to do is kind of take a look at what's going on when it comes out of charging. The first thing it does is some calisthenics to kind of stretch and make sure everything is working all right. It's a muscle beach kind of thing there. Hey, check out my biceps. And then after that movement, we'll end up seeing what it does with the legs. And so it comes down. Now, look at that. You see how the torso is able to look at that movement?
a little bit of the like flexion.
Yeah, they get it all there. Look at that. Look at that. Those feet are planted on the ground, and it was able to do a rotation. You see, you can rotate that upper body you can do it yourself at home. If you don't believe me, stand at home, plant your feet in there, and without actually twisting your torso, just try bringing it around. And you can say, "Holy cow, I can do that." So they are able to get that. Maybe not as much as you could with another bot that's going to twist itself around, but it might be enough for many applications, like, oh, I just got to reach a little bit into here. I just got to twist a little bit, or I want to move my head over that way a little bit. They can do it and still keep their feet in place. Now, I think any robot can do it because their legs are interesting legs. I mean, obviously you can see that, oh, it looks like the knee's backwards and everything else. And we've gone in this before. It's not actually the knee, that's actually the ankle. The knee's up higher and then the hip. But while this is has 6 actuators in it, it's actually a 7 degree of, or sorry, 7 jointed 6 DOF. So as far as degrees of control. And that is because this back link that you have there goes to a follower joint down here in the knee. So right there, there is rotation that is being kind of caused by the fact that this is connected up there. So they have a little bit more kind of movement in the leg, even if it only has 6 actuators like everyone else, but it actually is a 7 DOF, well, 7 jointed again. Most people would say 7 DOF, but let's stick with that. And that might give them in some a little bit more range of motion for a few things, perhaps, but I suspect not. I think a normal leg, you can do the same thing. So without a waist, you can rotate. Without a waist, you could definitely, go forward like this. And even without a waist, you can kind of rock a little bit back and forth. And if we go back, and maybe I should do that, is I'm going to quickly go back to that figure walking video that we had up right here. And what I want you to look at is you can see that the pelvis, because of the unlocking of the hip, is no longer horizontal to the ground. That pelvis is like doing this as they walk, and yet the torso remains horizontal. And so you can see the movement going through the waist on the X direction there. That X axis turns it because as those abductors and everything are going around, the pelvic bone is doing this, and you got to get a little bit of movement if you want to keep it level. So if I'm going to be serving drinks on a tray, I don't want to be doing this with the drinks, right? You want to make sure that they're not going to be spilled. So when you go, and now I can balance that easily by just going ahead and using my arms going kind of up and down is another way of keeping that level. But maybe it would just be easier if right from the beginning we make sure that we don't have the torso going back and forth. So that's your counter argument on do you want to have that or not want to have that. And
Wait, one question,
Mhm.
because now they have this demo for BMW. Would that be critical if they have this holding the parts and going around the factory? So I think they have to consider that,
No, no. I mean,
right?
for parts. I mean, again, I'm talking about this is going to be working in a restaurant, and you want to be, serving liquids, and you want them to be spilled or something like that. But for everything else, I don't think it's that important. So for what they're doing, it's not that critical. So again, look at your application. It is so important to think about your application and what you're doing to not put in joints that you do not need. If you need this general purpose one that's going to be working absolutely everywhere, maybe you need to put it in there, but it's going to come with a cost. And if your scale is going to be in an order of millions, you're going to be like, don't worry about it. That's going to cost pennies to put that thing in there. The main thing is that we can deploy it absolutely anywhere and we get a big space. But if someone comes in and says there's a very kind of focused application, that's all you're ever going to sell, then or area or domain that you're working in, then you might consider, do I need to have that? And that's where it comes kind of to a little bit of the conclusion of what's going on here is that if you look at the number of degrees of freedom in the waist, you can see there is, you know, while 3 might be the one with the highest number total overall. If you add everyone else up there, it's not. It's like definitely there's no decision right now on there's quite a few that are going with 0 degrees of freedom and quite a lot with 1. The 2 is you get 3 in there because we fudge it with the Y coming from the hip itself, but it's almost like a 3 degree of freedom if you want to put in there. Um, so you see they're all deciding that their waist designs have to be very focused to what is their application, and there's no, literally one size fits all in there and decisions. But a lot of it is going to be dictated by the hip design, no doubt about it. So if you don't have a far hip, you're probably going to have more degrees of freedom. If you do have a far hip, you can get away with 2 in the waist. And now you're talking about, really reducing the count overall and the number of joints that you're going to have, and the number of actuators, the amount of power is going to be consumed, everything else. So now, if we kind of look at all the different hip configurations, so now not just degrees of freedom, but all that are out there in this design space, you'll see of this design space that I've kind of come in, and there could be like more possibilities. You could just be dropping axes like crazy that you don't need to have out there. But we'll see kind of what the population looks like, and it's scattered. It's all over. There's no definitive conclusion on which is the best. We can see that these have not been explored. And they probably haven't been explored for good reasons. It's like it almost doesn't make sense. It's like I have basically what I'm saying here is like the capital YXZ hasn't been there because everyone's been doing it with a little y instead. And then that one there, it's just changing the order a little bit. And you go this way, it seems to be the preference is to do the X rotation and then the Z last. There's no reason why you couldn't do Z first and the X. So I'm not sure if there's any advantage to it, but those that are kind of exploring in this area, you see none of them have gone with the Z after the Y. It's always the very last one. So it might have to do for cabling and a bunch of other reasons that's very important. Um, and then again, a lot that are basically just Z because they all have a Y, and then these ones here basically are. I mean, you don't have anything. There's nothing there. You are getting something out of the pelvis, but as we have seen with agility, you could almost say it's lowercase XYZ because there is like some way of being able to get some of the movement you want just by moving your pelvis around. But it may come with a cost that your shoulders are now suddenly dipped to the side in order to bend left and right, or when you do that, your pelvis is going to have to be doing something with the strength. So okay, the that's kind of the bot configurations. And again, I was looking at what you can do with some of these different designs, and again, looking at Unitree and what they're doing with, and I think this is the full waist that they have here, and this was them doing, and it might have been like the first time this trick was done. So I think they, for that, it looks like they were using all the 3 degree of freedom waist, no doubt about that, and able to do it. And then again, if we want to kind of look, it's like, well, what if you want to do dancing, surely you need to have something there. Now, this is engine AI, and I don't think they have any degrees of freedom. I'm looking at it, and sometimes your eye gets tricked to thinking that maybe they have a Z, but I am not seeing any movement at all in the waist. Yet look at that. I mean, look at what they're able to do. I mean, and again, because with the abductors and stuff like that, they're able to lean left and right and do everything. Fairly good dance moves, even without that. So, so again, look at these things and come up with a decision and think to yourself, how much do you use your waist and all the activities you do? How much of is it actually in there for doing some things? Now, obviously, when I'm trying to fix the plumbing, under the sink, man, now I got to get myself the torches to get in there. That might be very important. But for everyday kind of things, maybe not.
But wait a second, what is holding it? Because is it stability thing?
It looks like they were doing something around people, and I think it's just there's a safety harness. So I think that's just there in case it falls down, because it looks like this is something that was probably grabbed. I don't know, maybe in their own lab or something like that, and they just want to make sure. And it does a pretty good job of staying up, even though it's getting twisted around. Yeah.
There's no waste, and they managed to do something.
Yeah,
Wait,
yeah, yeah. I'm pretty sure there's no waste, and if there is, they only have Z. You know, so they don't have the X, and they have the Y, but they have a far hip design, which probably allows them to be able to do that. And again, they changed their hip design from the original one, so they learned a lot from that. They stayed without a torso. They decided right off out of the gate, we're not going to have a torso. They're building these things, and they're probably convincing themselves we don't need a torso with the things that we're going to be doing, or I should say, a waist. We don't need to actually have waist joints. Uh, and so, yeah, I encourage everyone that's working out there to rethink of these things, to kind of look at it, challenge your assumptions, just go through and challenge your assumptions again and again and again to be able to make sure that they're okay. Some of this you can do in simulation. You don't have to necessarily build the hardware, and some of it can be just thought experiments, and you really go through it and try
let
working
me
it out
ask
that way.
you. Let me ask you, if a figure, for example,
Mhm.
is going to remove the waist, that means you have to change the configuration of the hip, right? Or is not
Uh,
necessarily the case?
yeah. So I think if You may not have to. I mean, it would just be a matter of like, oh, we'll take one or two of those joints out. So they could take. Now, what might happen is that you have to retrain a lot of things. So as and it may be easy. The question is, if you change your embodiment too much, can the data you get from the last one work that well into it? So these are questions you want to answer very very early on of whether I take something out and be really confident that you can take it out because you have to put it back in and maybe all the training data you use is kind of lost. This is also, one of those kind of concerns I have now is I know everyone wants to do reinforcement learning when it comes to hands. So that's the next area to go into. And it was pointed out in the figure white paper, and I encourage everyone to go in there, take a look at that paper. And and that was about how they did the walking in the reinforcement learning. And one of the problems you have is like always being able to take everything you learn these things and then put it into real hardware. So in order to do that, your simulation just has to be good. And your simulation just can't be kinematic. It has to be physics based. You have to really understand how the actuators and model that correctly. So you've got to have a good model. Now, the cleaner your design, the easier that is to do. The more kind of joints and in kind of remote actuators that you have or things like that makes it a lot harder because now you have to model all those joints and all the friction, everything that's kind of in there. So if your in and outputs are pretty clean, it becomes a lot easier to be able to do that. To get it right, you got to get the physics, you got to have your friction right, you've got to have your moments of inertia, all that you've got to have that down. Your gear ratios, the way they're going to work, and then you go in, and then now you want to take it and move it over to the real boss. And of course, the whole idea is that whatever you put in there, you can put in any numbers that you want in RL. But if they don't match the actual mass distributions that you have in your bot, it's probably going to have a little bit of problems there. So, but you try to get as close as possible. And a lot of times you'll be reasonably successful and it's close enough and it will adapt to it. So what Figure did is they said, well, we realize that no two actuators are going to be the same. We're going to build as many of these things as we can and we want them to be one sub spec, but they can never be exactly the same. That's the thing with all manufacturing is you go to the store and you buy a bunch of half gallon. Yeah, I'll guarantee you some of those half gallons of milk are a bit more than a half gallon, and some a little bit less. Okay, as much as they try to make within there, there's always going to be a little bit of error. Same thing with building a bot. There's going to be errors everywhere, and the question is, you know, how much can you constrain those things, and then you train on that. So when you get that neural net and put it over, it doesn't matter that that body that it's in is different than the ideal body. So they intentionally make sure they have pretty good size design envelope and that they're the zero shot. So they were able to zero shot that. And what was impressive is that not only did they get to work on one bot, but they then sent it to 10 bots and it worked. And that's one of the reasons why you'd like to make all your bots as close to identical as possible. If you start changing that configuration, it's like, oh my goodness, we're going to have to do this again. So Figured is going to be sitting on a bot that's 5'6". They're not going to say, oh, you can order 5'8" or 5'9". It's like, no, it's like, this is the size it's going to be for now. Eventually, as we get better at these things and understand how to do it, they'll be able to scale these things up. But for now, it's like, we're literally, for one size fit all, we don't want to change the whole things. Now, when it comes to a hand and you want to start doing that for manipulation on the task, it's going to be more of a challenge depending upon the type of hand design you have. Like the more degrees of freedom, the harder it's going to be. And again, it comes down to the key of how well you can simulate the physics of what's going on in your hand design. That when you move a motor, how does it react and everything else? Tendons have all kinds of problems. One, it's very, very hard to build two identical hands with the same tendons that are going to have, everyone's, part of it is that tendon stretch. Yes, it's Kevlar and these aramids that don't stretch or have very little stretch in there, and hopefully their properties don't change with temperature and everything else. But there's also manufacturing tolerances. You just cannot produce those fibers to be always exactly the same. They'll be close, but they won't be exactly the same. And then, connecting it, getting the lace, getting all that stuff in there is the same thing. And then the friction that's going on. So you're pulling down here, having a bunch of things that are going up here. There's a lot of friction, there's a lot of sliding and everything else. You don't have any information to know what's going on in there to be able to understand what that movement is like. And this is the problem that they're going to have is you're going to need a super good physical model for the tendons to be able to figure out how the head is going. Now, if you go to more to a mechanical hand, which is something that the Figure has, I think Peng has got that one, and Unitree just shown one. And I think even Boston Dynamics looks like a very mechanical hand. So a lot of them are that way. They'll be a lot easier to simulate those things. And we're going to do another episode on this, but just kind of the teaser is that the Unitree hand that came out that they showed like yesterday, or the day before. I was blown away again by the specs because they're really open about that, and they get the degrees of freedom right. It's a 16 degree of freedom hand, which does that mean, oh, 16 degree freedom? It means it doesn't have as many degrees of freedom as a Tesla 20. It's like, no, no, it's a 20 jointed hand with 16 degrees, meaning 16 actuators. The Tesla hand is 22 off, but only because it's got like the movement here down the pinky. Um, so it's equivalently the same, but they're using way more actuators. They're using like 24 actuators to do it because when you're using tendons, tendons only allow you to drive your finger in one direction. When you have an actuator that's directly connected to your finger, it can go positive and negative. So I have a smaller number, but the main thing is like their control parameters were short. It's like absolutely insane. For each joint, for each knuckle, they have not only the position, the velocity, the torque, temperature, and that's not even including their sensors. They have an IMU in there. So that basically the IMU means I really know kind of how my whole hand is moving. So it's like, wow, that's information I hadn't even thought about. So the richness of the data you have there is going to be absolutely incredible. Just something that's very, very hard to extract from a tendon-based hand. It's going to be really, really hard. Because when I pull on a tendon down here, it can't tell me what the angle of that knuckle is. It can't. I know what the tension is, but I have no idea what that angle is. Probably have no idea what the velocity is or any of that. You can try working simulations. I might guess what it is, but you know, Unitree will tell you right at that knuckle exactly what the angle is, exactly what the velocity is, exactly what the torque. That is like a lot of information. So when you start going around grabbing objects, you start getting information. And so this is why I put out a post, and then some people flame me on it because I said, rip anyone that's using tendon fingers. And they're like, oh, look at me. And it's like, okay, yeah, I know you have that. But
How one X reacting to that? One
yeah, I
X.
mean, there's some people that thought it was interesting, and others like, oh no, it's like, you know, I've got my tendon based hand. And we talked about this briefly yesterday, is that you can get inspiration from nature, but don't take it too far. Okay. So um nature does not have a door hinge, okay? Because it's something you can't make. It's something we make mechanically, and it's actually kind of superior to the joints that nature has come up with. And nature's had to do all sorts of things to have what's effectively a hinge mechanism, with ligaments and all these other things trying to hold it in there to have basically these two joints that roll on top of each other. So it's a lot easier to design it that way. Now, again, when the inspiration for being able to build airplanes is because we can look around and nature is showing us, look, you can fly. It's possible. Well, how do they fly? It's because birds have wings. It's like, okay, they get wings. What about the shape of the wings? You know, and it turned out like from that, and you know, going back to Leonardo da Vinci, you know, maybe even earlier, they understood a bit how that worked. Lilienthal then took it a bit further with his gliders. And the Wright brothers were looking at that and say, yeah, but the one problem we have is like controlled flight. It's like, how do we turn this thing? And they study the birds. They go, guess what? They do wing warping. That effect. So they get inspiration from that. That was absolutely great. Okay. However, how do birds actually propel themselves through the air? They flap their wings, right? All right. If nature is so good, why do all our airplanes have jet engines or propellers on them? They don't flap their wings. And yeah, I know there's some drones out there and some people who watch Dune and say, well, I get the ornithopters in there. They're like, it's like, yeah, they're just not efficient. Okay. We put propellers on there because they're superior. Nature didn't come up with a propeller because there was like no way for a biological system to come up with something like that that makes sense. Now there might be like some flagella and some bacterium here and that. There's something similar to that, but at the macro scale, it was just like nature couldn't figure it out. The best thing was to flap the wings. We took the inspiration and said that's better. And this is the thing is like the hand may be a brilliant idea from nature. And the only way nature could do it is that they need to do the tendon actuation, you get the muscles and everything else back there. It doesn't necessarily mean that that's the way a robotic hand has to be done. That, you know, this idea of going more mechanical and actually them locally. And now what Unitree did is it looks like they made these micro drives that literally they have like little motors there. Can be some downsides to that. The first downside is they it doesn't seem to have the grip strength that you would like to have. So the grip strength is very light, and based on that, it's like you could not pick up your carry-on luggage with it. You know, it wouldn't have the grip strength from that. So that's just kind of an example. It's in the order of like 3.5 kilograms, I think, is what the grip is. And if I recall, carry-on bags are like 8 kilograms, something like that. So it's about half of what you would need just for something of that lightness. Um, But that's only gonna get better with time. It's like they're taking the first step. The hand isn't perfect. I'm looking, it's like, oh, okay, there's obviously a little rough. It's like, okay, because they just started this thing, they're gonna get better and better on it. Um, and so if they can improve the torque on that'll be something. And the other question is just gonna be durability. So when it comes down to the hand designs right now, if you're gonna judge them, the first thing people are gonna say is, is it durable and reliable, and what's the strength like? It's gonna have good grip strength. There's no doubt about that. Otherwise, it's a non-starter. Um, but as we evolve these things over time, it's a very interesting design. And I'm glad to see that they're doing it and they're taking on that challenge. I hope others take on that challenge because I'm a little concerned that I know there's some smart people working on the tendons, but I have a feeling they're going to run into some issues as they begin to realize how finicky tendons are, and that they don't give you the information, and then they might find out that, oh, we're going to have to start instrumenting all our knuckles to get the information about what's going on. When it's like, well, if you just had a motor drive right there, basically it's already instrumented. It's got all the information that you need to come from it. So yeah, that's a little bit of I won't give away the game on what that episode will be like. The
No, I think it's a I have to say this was super, super interesting episode.
Okay.
Um, and I think it just, as you say, it depends on application. It seemed that agility, they managed to do its great stuff.
Yeah, 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 yeah,
AGI managed to do great stuff without a waste.
yeah,
So it comes down, what do you need out of that? So it's
yeah.
up to your designing process
Exactly,
and
exactly.
that,
And that's the thing is that um everyone wants to know what's the correct answer. And the thing is, there is no correct answer. It's what's the correct answer for your application. And that's what's important is knowing what it is you're trying to do. And I'm just trying to encourage anyone that's moving in that space to really think about it. We're going to do probably another one at some point where we talk about ranking and everything else. That's like, if you can't explain it, you can't do it.
but let me ask you, do you think any of these humanoid robotics company did something like over-engineer is not needed? Did you notice any of them? They over-engineered the design.
I haven't I don't think I've seen that. I see it seems like they've been very careful to not put that in there. Going back to the very beginning, the comment about, the bots being able to walk. Um, it almost seems like I think you over engineered it by putting the rotational axis in your legs since you don't seem to be using it. It's just like they hadn't got to the point of unlocking that. But so they clearly knew that was going to it was going to be needed. Um, the other thing when we get into the shoulder, there'll be questions like, do you need all 3 degrees of freedom there? Yes or no? And they've studied it enough that you could argue you could take away a degree of freedom from the arm. You could argue to take away a degree, but you really need it. And it's not so much that it's the safe call, it's actually the right call. And over engineering the leg would be if you have a 3 degree of freedom ankle. I mean, we already talked about that. I said one of those joints is absolutely toxic. The one place where they may have actually over engineered is in the waist, which is what we're talking about. In some cases, that they may have too many degrees of freedom there that could be removed. And then the question is going to also be in the head. Do you really need a 3 degree freedom head when you see them out there? It's like, is it that important? And even 2 degrees of freedom. Really think about it. Now, the two DOF head is really going to come down to what they want to do with the camera system. So if they're finding that they only need to look up and down, then that should be the only thing they have. They shouldn't do anything like that. But they may be finding that from using it that the head has to turn to see something. That may be a very important thing. In which case the two will be there. And right now, I think it's the right call to go with 2 degrees of freedom in the head. It might be that you can get away with one, but to be fully kind of general, it seems to be there. In the figure example, they put the ketchup in and the bot's turning your head going up there looking at it, kind of convinced me, oh yeah, it looks like you need both. You just can't turn. You got to also kind of look up sometimes. So, but yeah, I don't think anyone has like fully. Oh, okay, what is it? Fully, maybe clone. It's like whoa, that's in a good way. Okay, I'm not trying to show it.
Yes, I'm just thinking when I say Colombia, we interviewed well, I had a podcast with CEO I think 3 years ago, but I'm just wondering what would be the use case. Yes, it's impressive, but where would be?
Event. Well, I think it's been pointed out that a lot of the inspiration by many people building these humanoid bots is like elder care, is being nursing and in the home kind of medical care, and the idea of having these cold, stiff mechanical hands touching you or something like that. Just like they want to have something that's more human-like. And I could see that, and, I can understand now. It's like, "God, I can't quite see, it seems like all these other bots will be good enough the way they are. Why do you really need to do it?" And I guess you could say that about any form of research. A lot of people have researched something like, the transistor. What's the point of that? We don't need that. Do we good vacuum tubes? It's only years later that you begin to see the benefit. And that's why, I really like what they're doing at Cologne, because it's bold what they're trying to do. It's almost crazy what they're doing. But the what we're going to learn from that research project, and hopefully it turns out more than a research project, that they actually able to come up with something that's commercially viable, is going to be invaluable to the overall industry eventually. So we don't have the technology to produce what they want to do yet, and the only way you get there is by doing the hard work, and maybe by the mid 2030s, something like that becomes viable. But we know if we want something working in the factories, in the next couple of years, that's not going to be the approach for now. And of course, they're probably, down there in the comment section right now saying, he's completely wrong. Just wait until 2027. He'll show you something. So, and I'll help him wrong. And I hope they're right. Uh, but I got one last little uh, extra here, bonus. And this is that, when I went for a walk yesterday, I took this picture because I looked at it, and, being a nerd, I'm like, oh, look at that. That's exactly how the Optimus knee works. So if you look down here on the shovel part of the excavator here, if you ever wondered how this unit works, it's exactly the way the X-Peng and also the Optimus knee works. And this is what they call modified Hertens, a 4-bar linkage. So you can see 1, 2, 3, 4 points here, or if you want to look at the edges that connect it, that's your 4-bar mechanism. And the Herkins is,
The episode we did before.
yeah, yeah, we talked about that. And this is one where I think there's some magical relationship between them. They're almost like the same length or something like that. And the main thing was like, it was a mechanism that as you rotated it, traced out a straight line. Now the purpose of this is not to put out a straight line. The idea is to make sure that the torque is kind of linear as you go around on this. So when you have the shovel, you want to make sure you're able to apply the same amount of torque the whole time, and it doesn't change as a function of angle, which is typically is what it would do. And then, of course, with any sort of excavator, you're using hydraulic. You get this hydraulic cylinder, which is very important to getting this thing to work. And it's got a pin joint up here, so it has to rotate up here, and as you can see, it extends out. And hydraulic cylinders, they produce a lot of power at a distance. And remember, the motor for this thing is like way off on the side somewhere. It's actually the diesel engine of the excavator. And with hydraulic fluid, you're able to generate a lot of force, which extends this piston out, which then creates the moment arm around here, and it does it in a very linear fashion. So that's the reason why they built it the way that they did, is so the excavator could do that. And again, this is how those knees work, and the reason why they went with those designs. And also the Artemis from Romella Labs in UCLA. I mean, because I think they were the first ones that really kind of push it, had a paper out there. That's from Dennis Hong's group.
We had a paper, you should, we had a paper of that
Yep, yep,
also.
yep. And then if you look up here, you'll see the elbow. In this case, it's a 3-bar mechanism, where we can't see the pin joint on here because I didn't frame the picture quite right. I was like more focused on this and realized, oh, I've got the other example up there. And you can see how the elbow mechanism works. And this is simpler, because you don't have this complicated 4-bar mechanism built in up here in order to make the torque kind of consistently go around. In this case, the torque goes as a function of this angle. So when it's in that position there, basically when this is almost like perpendicular to the lever arm, you got the most torque. And then as you start pushing it forward, your torque goes down. You start losing torque there. And then when you straighten it out too much, and oh, okay, this was like, just so you can get another view. Let me kind of go back to where we was seeing it. Uh, and that's how that works. And then again, that's how the elbow and a couple of robotic arms. Apollo does that. I think the iron also does it, and also Optimus, of course. And I think there are a few others that use that mechanism. And that mechanism you'll see on your doors, that keeps the door from closing too quickly or something like that, is also kind of a similar mechanism like that. But yeah, so that's just like the bonus that sometimes when you walk around, you will see something, and then you should say, "Aha, I've seen that before." And what is it? That's the
I love
mind
the
of a
fact
nerd.
that I love the fact you're wondering and then you saw something just absolutely similar that we have it. So
Yeah, yeah, yeah,
that was great.
Yeah, yeah, so this next time you see one of those excavators out there, I mean, study and watch it and you'll understand it. And since we've all seen this, you're like, "Oh, okay, now I finally get it. And now I see why they built it." Because it's not so obvious why it's built that way, but when you see this thing here and understand how it works, it's like, "Okay, that is a day-to-day kind of thing."
Yep. That's just awesome. Again, I think it was excellent episode. I think you first of all, I want to appreciate the fact that about the design from an inspiration from nature. I think that's very important. Listen, that you don't have to copy the nature
Yeah.
exactly as it is.
Yes.
You have to think it twice whether it's needed or not. Or maybe I think that yeah, this is very important lesson, and yeah, I'm not sure what will be the future of the waste. For example, I'm not sure the again a limited application, but I'm not sure the future iteration will be the tendency toward eliminating the waste and just focus on something simple.
Maybe. And again, if we're gonna follow nature, then, "Oh, let's build a full spine, full segmented spine." Like, "Oh, good luck on that." That'll be tricky. And yes, there are animatronics that have done it, Hollywood designers that are very clever on that. And I think the way they did is they also kind of use tendons or cables to be able to create a spine mechanism to come up with, some sort of doll that looks very human-like. And if you want something that's extremely human-like, yeah, you're probably gonna have to do that. But if you want to have something that's just able to be worker bee, I don't see the need for a spine.
Do you know the Spider-Man is Stuntronics? I did an episode with the designers from Disney. I don't know if you know them.
Oh no, haven't seen that.
Yeah,
That
this
could
was
be
also
pretty
2 years
because
ago or something, and they managed to launch the Spider-Man Stuntronics. It just
Oh, yeah, yeah, yeah. I think I saw that. That's absolutely fascinating. That Spider-Man, yeah,
and
exactly.
it's just
Yeah.
one link mechanism, it's one bar mechanism. I think they did this like one
Yep.
link because, but I think this is was just guided launching.
Yes. Yeah, and I think part of it's just using the physics that it gets snapped around and it just kind of is able to follow a few things. And I think it's also stiff in the plane. They're not having to do anything else. So if you add a full spine in there, but yeah, you can well, if you go into any anatomy lab, they'll have a skeleton hanging up there, and you can see the whole spine of the vertebrae. They're all being held together with wires to kind of keep them in place. And so you could do this, so the same thing. You make a mechanism like that, then you got some cables that, depending on how you pull on it, it'll either go this way or that way, and that because of the tension, and it'll do the same thing with kind of like what our finger does. Because our finger is just like a mini version of our spine, in that you're kind of pulling on something, and that all of them have to move along with it, and your spine is just segmented and has a lot more segments in there.
Okay, awesome. So I can't wait to the next part of the humanoid robot. I think I'm not sure if you would like to hear suggestion from the audience or just to you decide. I'm not sure what do you think. Should we ask what's next?
Oh yeah, 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 yeah. Let's see the yeah. Why not? Whether to go in the hand, I'll be moving up the list and getting to the shoulder, and then after the shoulder, I'm gonna be treating a little bit about the ball and socket, and because the shoulder and the hip, there's some similarities there. Um, but let's say the industry trends are like definitely very clear what the solution was there versus what it was originally for the hip. And then, again, kind of going through the whole ranking exercise again that we sort of talked about in the in out, but I'd like to look at it as like, yeah, clearly start thinking about if you had to rank every single joint in one of the limbs, could you do that? I mean, would you have a hard time doing that and deciding what is the most important in that? And hopefully by now you probably can if you just kind of listen to how I've talked about some different joints. You may have an idea of what they are, and then I would like everyone to really think it through and challenge my assumptions to see if I'm right or wrong. Okay, because that's the whole point, is to get you to go through the thought experiment.
Well, this series is quite rich and super interesting. I can't wait for the next one very soon. Thank you, Scott.
Hmm. Okay, yeah, you're welcome, Mara.